Okay, good morning. So we will have the proof for this one. Acceptance rejection. All right, so maybe let us review this. So acceptance rejection says, if I want to generate random variable x, in fact, we need to pass on the majorizing function. Majorizing function will have a random variable y. So if so, we will have the random variable y first. Follow the density R coming from the majorizing function. And we have a u further. U will need to determine, should we pass on y to have the output? Oh, if no, here, greater than this, then no. No, then we need to repeat the procedure. So we want to pull this. If we want to pull this, here, this is the way to have the random variable. Only acceptance of y, and then we use y. So here we have acceptance. All right, only acceptance, then pass on y. Y lower than or equal to x. Well, if so, then we have the this one actually is total theorem of total probability. Okay, so this is a theorem of total probability. All right, so y lower than or equal to x, and then we can pass on value of y. Pass on value of y, we need to multiply the corresponding PDF, and we have the integral, so this is a theorem of total probability. Once we have this, then we check. All right, so here we have the range y lower than or equal to x. Same. All right, but right now, y actually from negative infinity to x. And next one, it's x to infinity. So we have the two terms. If we have the two terms, y lower than or equal to x. And how about this one? This one actually we have the range y greater than. So this one is y greater than x. Actually it can be equal, but if we have the continuous random variable, then we should have a 0 when we have the equality. So this one greater than, that says not the case, right? Not the case. So actually for this one, not the case. So if not the case, it's 0. Therefore, finally 0, so we can remove this. So that's why we have negative infinity to x. If so, then pass on this one. Oh, okay. This is the range we want to have, lower than or equal to x. Acceptance. So if it is acceptance, then look at this. Majorizing function. It's majorizing function. It's f over t. All right. So maybe let me check it again. Majorizing function, okay, so sorry. So majorizing function is t, and this is the original f of x, and we have acceptance. So this one, probability to accept. And this one over C here. Sorry. So this one is majorizing function. Sorry. This is a probability to accept. And the T over C is R of Y. So based on this, we can have the result. R of Y actually is T of Y over C. And the acceptance actually is F of Y. All right. So if we have this, we can cancel T. And here we have F of Y from negative infinity to F. So it's CDF. And CDF over C. So this is the current derivation if we consider this one first. So if we consider this one, then we have the result. All right, so actually we have this formula. But acceptance, only acceptance will have the result. So if we have acceptance, then we have the conditional probability. And then numerator, right now we have the numerator. And later we will have the denominator. And then we will have the probability of acceptance. But look at this. Currently, we already have the derivation for acceptance and y lower than or equal to s. Finally, we have the result, CDF of s over c. About this, I think right now I ask all of you to have the discussion for 2 minutes to check. Any questions? So you can rearrange the seats. So good one, maybe rotate. And this get closer. So let me make sure about the current derivation. Is it okay? All right, so if it is okay, right now we have the probability for the numerator. And right now, double check denominator acceptance. Acceptance, same, we can pass on the theorem of total probability given y. And given y, same acceptance. So we have acceptance of this one. And here, this is a T over C. And likewise, we have the result. Cancel and cancel, but this time, this is the entire range. If we have the entire range, so it's 1 over C. So we have the results, probability, acceptance. If so, this one, I think, previously, if you know the result, I think it's easy. So this time, I already have the result directly. Generate S lower than or equal to this one. Actually, based on the previous derivation, we will have the numerator over the denominator. So that it's f of S over C and 1 over C. So finally, this one. So this is the CDF desired. CDF desired actually is equal to the CDF of we set. Okay, so this is the result as desired. So we can prove it. So we can pass on the way to prove it, right? So finally, as desired, so this is a correct algorithm. All right, so this is a proof for the acceptance rejection algorithm. So that we can apply that one. All right, so about this, I think okay, right? So let me continue. And the following, we have the example. Previously, we didn't have the example, but we just use it to illustrate, oh, okay, we will have the range to accept or to reject. And right now, we have the example. You can refer to table of chapter 6 to have a beta 4 and 3. And so that we have the given formula. And the given formula, we have the shape like this. And how to have the majorizing function. In fact, if you can pass out the function, possibly, for example, you can use MATLAB. Or maybe you can pass out Mathematica. All right, MATLAB or Mathematica, then you can find, okay, where you have the maximum value. Okay, here we have the given result. And this density, we will find the maximum value, it should be this, C. And so that we can set function t of x here. And we use the simple one. If it's a simple one, then we have r of x here. It's equal to 1 because we can see the range from 0 to 1 for beta. If so, then we choose majorizing function, this one, and the r of x here. And so that we can follow the algorithm, generate y. And the y here right now, it's this one, f over t. So f over t, so we have the result, f over t. Generate u, and the u lower than the ratio, then we can return x equal to y and stop. Or otherwise, we need to repeat the procedure until we can have the acceptance. All right, so this example, I think is trivial, right? Even it's trivial, but look at this for 1 minute. Later, if any question, you just let me know. Okay, so for the example, it's okay, right? However, we didn't have the probability. Acceptance, the probability of acceptance is 0.48. Where we have acceptance, look at this. Actually, we can have many u, the value of u. And u fall above, then reject. Only this one accept. All right, so this is a direct implementation. If we have a value of u fall above and fall below, and then we can have reject or accept. And currently, the current region, the probability to accept, where we have a probability of accept, actually it's area over f, covered by f, and then the probability is 0.48. It's low, right? If it's low, then it takes a long time to have the generation of the random value. If we don't like it, we can find a tighter so we can have a tighter majorizing function. Majorizing function. And here we can try to find, oh, okay, possibly looks like this way. If we have a way like this, and then we can have a probability of acceptance higher. Right? So the probability becomes higher. Why? Majorizing function and f of x, the ratio actually it's large. It's large and then it's easy to accept. So of course, this one we will have a higher acceptance probability. However, you need to have the suitable way to define majorizing function t of x here. Okay, so this is the result. And finally, check this. Higher acceptance probability. But previously, if it's the original majorizing function, easy to generate y. But this time, this one, a bit harder to generate y. All right. Finally, if we have this way, beta, actually it's a trial. So it doesn't mean if we have the simple one and higher rejection, it's bad, no. And here, this one is good, maybe no. You can have the balance. Finally, okay, I prefer that one. For example, if we want to have a low acceptance probability, we prefer this one. All right, but this one you need to have the sacrifice of a bit harder way to generate y, so that this is a bit complicated function r of x, and that's it. So beta actually just a balance. So it doesn't matter if you prefer this one, that's fine. You can find it and use it to generate the random variable based on the acceptance rejection approach. Actually, this is a further discussion talking about the squeeze method, but I skip it. All right, so for this one, I skip it totally. It says, okay, sometimes we can have this way to have the further discussion, but I skip it. So this is the acceptance rejection algorithm. I think it's okay, right? So if it is okay, then next one, we have the next approach, ratio of uniforms method. All right, and this method follow the way here. This one may be somewhat complicated. And where we can apply these, this time we don't have the proof. So you can find the proof for yourself. Not covered in the textbook, no. And actually, we will have more description, so you can check the current range so that you can find a further discussion. So this is the uniform ratio of a uniform method. So I just let you know, and same mentioned, but we go through quickly. Finally, we have a special property. What it means, special property. In supplements to chapter 4, we already have many properties. And those properties can help us. If we can apply one of those properties, then we call special property. For example, example 1, geometry. And geometry, actually, we have the probability P to have the success. Or otherwise, actually, we have a failure. And here we have S to denote number of failure before the first success. If we want to do so, then we have the special property. We can pass on, here it's a geometry, but we can pass on Bernoulli. Bernoulli, you can try, okay, number of failure. So you can try probability P. Okay, failure. Okay, you can collect number of failure based on Bernoulli. And so that you can have the implementation. Why? Based on this one, you can have the implementation because Bernoulli seems to be easy, right? To test. Okay, to test it, how to have the result actually based on uniform. Uniform lower than or equal to P, then it's success, or otherwise it's failure. So we can pass on the way to generate Bernoulli. And way to generate Bernoulli, then we can know failures or success. We need to collect numbers of failures. So this one, it's the special property. The special property between geometry and Bernoulli, right? So this is the results covered in, actually you can find it in chapter 6. Or maybe you can refer to some other reference to know this. And next one, beta. We already know the fact. Gamma and gamma, then we have the ratio. The ratio, it's beta with the parameter alpha sub 1 and alpha sub 2. So likewise, again, this is a special property. The special property says if we have the previous beta, and right now, how about generate gamma and gamma using the ratio? It's okay, but you should understand, later we can know to generate gamma random variable. What is the way to generate? Likewise, it's acceptance rejection. Not easy, not easy. But if we have the way to generate gamma and we follow, then okay, it's easy. Even to generate gamma, it's not easy. Still, we can pass on the special property. So this is the second special property. All right, so almost all, and this time I have a new name for this of the poll to ask you, up to now, where are you feeling challenged? I mean, any difficulty? That you have for 1 minute to fill in, and later let me check any possible question. If no, then we can move on. So go and check it. But before you go, let me make sure, Enzo, everything's okay about this. Poll everywhere. So can you see it? Good. So later I will check the result, but respond to the poll first. And meanwhile, let me mention, follow the schedule when we have the so-called final exam 2 weeks later, right? You can check the schedule. So of course you need to review. Actually, we already have the self-exercise. We already have the problem set. You can try to use them to have the practice. And we'll almost finish the chapter 8. So of course you need to review chapter 1, 2, 4, supplements 6 and 8. And the style of the final exam, we allow you to have an A4 page to have the formula. Formula only, not the results of the problem. I mean the solution to the problem. Just a formula. You can use A4 to have 2 sides to have the formula there. And initially, I allow you to half of time using the closed book style to answer. And the second part, I allow you to look up your A4 page. All right, so you can prepare these. All right, so let me make sure not finished, and then raise your hands. So finish, then let me check. Oh, okay, good. No difficulties. Yeah, it's true. Deriving equations, that says proof, right? If so, then I think you just follow and recheck. Okay, about the good discussion, sure. Sometimes I just push you to think about that because sometimes I already have the exam, the questions, right? So for some good discussion, I push you to check. Okay, not feeling particularly challenged. That's good. All right, so I think maybe 2 questions here, maybe about good discussion. And of course, I know about the proof of some derivations. But at this moment, I think almost most of you can follow. I think that's fine. All right, that's good. So let me move on to the next one. Right now, we have the way to generate random variables based on the previous methodologies. So how to do. And later, I just mentioned the approach. Maybe for some example, I can let you try. So first of all, uniform. Uniform, actually, we can pass on the way it's the inverse transform, right? Inverse transform, right now, that you have 2 minutes to check. Is it true? Can we use this? So for all of you, you try it, and later I try to make sure how many students can have the algorithm for uniform. It's trivial one, but I ask you to practice. Do not follow the current content. You just pass on your way to derive inverse transform for uniform. of course, feel free to discuss, and so that maybe at least you can have the answer like this. So the goal here. So let me check. So anyone can find the algorithm exactly? Okay, no. So the key should be what's CDF. Once you have a CDF, how to do? Then we will have the results. So how to have the CDF? So we think about same 2 minutes again. Bonnie, can you find f of x? If yes, and then you can solve it. So allow you to have the extra 2 minutes again. This one actually is similar to exponential, but it's not exponential, it's uniform. So let me check again. Currently, can you derive CDF? If yes, raise your hands. Ulis, okay. And Ulis, can you derive the algorithm? Or maybe let me have for the first step. Can you derive x here? So that's easy, right? So you can have for the algorithm. So Santari, can you have for x? And then can you have for this? It's trivial, right? Generate U. And U follow the formula to generate, right? U. That's all. So How to have a CDF? It's easy. A to B. So what's the label? The label should be 1 over B minus A. And find CDF, you just need to perform integral. And based on the boundary condition A and B. A, we have a 0. B, we have a 1 because of a CDF, right? And so that you can find f of s. Once you have f of s, you can have the equation. Solve the equation, then you should have the formula so that you can have this algorithm. So just follow the same way inverse transform method. But inverse transform method, the first thing you should have is CDF. How to derive CDF, and then if you can have the CDF, and then you can have the result. The result says inverse transform generate U and return the so-called S based on the formula you derive, and that's all. So you can check it, is it true? Inverse transform. So this time, allow you to have a 1 minute since to be. You need to check what's the definition of an inverse transform. So you can pass on your slides to find the algorithm of an inverse transform. So go and check it. Refresh your memory. What's the inverse transform algorithm? So you have slides. Therefore, you can feel free to check the slides to know how to have the algorithm for generating any random variable using the method, inverse transform method. So let me make sure, Tobias. So can you find the inverse transform method algorithm? Yes, right. And if? Okay, so know the way to generate inverse transform method, right? And can. Okay, so this is a way inverse transform method. We need to repeat if indeed we want to apply. So let me mention one thing again. 2 weeks later, possibly if we can finish chapter 8, maybe at least before next week, then we have the so-called final exam. Because next week we will have the case study. All right, and maybe we cannot finish all this week, but almost done for chapter 8. And the range is chapter 1, chapter 2, chapter 4, and supplements of chapter 4. You know, we have a supplement, even previously we have the 3D classroom, am I right? And chapter 6 and chapter 8. The style of the exam, half of time it's closed book. And for the remaining time, it's simply we call open book. By open book, open your A4 page only. And you can bring your A4 page. And of course, before you use it, I will check it. If acceptable, then you can use it. When it is not acceptable, if you write any solution on the A4 page, not acceptable. Okay, so just the formula, not the solutions. And maybe some of you feel, oh, okay, Professor, about good discussion, sometimes somewhat difficult because I allow you to have the practice for some problems, right? And for those, actually, we will have the release solution, so you can refer to those. And maybe some I will already have the solution because we have some extra problems. And I try to that all of you to have. Specifically, if we have a partly, I will try to that have the solutions there. So you can check partly to have the solutions for the specific problem as well. And also, the problems, for example, for the good discussion will be covered for the final exam. So to check some of the problems. If you fail to notice some of the problem, recently I tried to provide the slides video for you. You can check, okay, where you have some video, and then you can check the problem and check some discussions, check some results there. All right, so that's why I think maybe yesterday you find some of a video released by me, right, about computer simulation. Even previously you have the train video, but I try to slice them to 5 to 15 minutes. Maybe sometimes a bit longer and sometimes a bit shorter. But you can try to find it if you want to have the quick check. All right, so inverse transform. And from exponential to well-bound and right now to uniform distribution. I think previously you know the general algorithm of inverse transform method. So this one, we check exponential m stage ln gamma well-bound. So actually you know how to generate well-bound and exponential this time. Let me go through and skip them. Exponential and well-bound done, right? Right? The previous example we have it. And actually this one convolution is done as well. And only gamma. Later we can show you how to use gamma. And actually for gamma we use a subtext rejection. So this time we don't have it. But we will have a normal. And once we have a normal, we can pass on normal to have a log normal. So log normal is easy. Generate normal. If we have the corresponding parameter, then this way is log normal. So this one almost done. And beta we pass on special properties. So we will check some of them later. So first of all, exponential. Finished, right? So there you have it, and we'll go to the next one. But I mentioned this. One minus a and u. If we have the expression in terms of 1 minus u, we can replace 1 minus u by u. So this is a trick. Why we want to replace 1 minus by u? Actually, we try to reduce the operation. Even it's one more operation, but we try to reduce the operation minus. And m stage order, actually, in the previous discussion, we based on this, right? So this formula actually is convolution, right? So finally, we pass on convolution. It's done. And gamma, we don't have it, but we show you the method. The method actually based on acceptance rejection. To have a acceptance rejection, we have two cases. Alpha greater than 1 and alpha lower than 1, we have two cases. And I just studied half of the two cases. And maybe currently we have this. I go through this quickly. And actually based on acceptance rejection. So you see acceptance rejection. First version, if we have a value for case 1 alpha, and likewise case 2 alpha. So we have the specific cases. So in the following, I just ask you to check some of the content. If you have the slides, you can check slides. If no, then you can take a picture for these first. The first picture, you can take a picture. Later, you can check these. First one. Okay. And second one. All right. And third one. The different one, take a picture again. And the result for gamma. So pass out the 4. I allow you to have 5 minutes to check or maybe discuss with your neighbors how we can apply acceptance rejection to have the algorithm. Actually, you can check first 2 pages, then you can know acceptance rejection. But just go through. But if you want to derive it, maybe later you can check it. So right now, let me ask you to rearrange your seats again. So group 1, maybe 2. And you can rotate. And yeah, it's true. Okay. And for group 5, maybe rearrange your seats. And group 4. So Vincent, actually, you stay there. It doesn't mean you need to rotate. You still sit like them. And so that it's easy, right? But in between 2 of them. So 5 minutes to discuss. At least you can check the first 2 pages. We have 2 cases, at least you need to check. So that later, let me know everything's okay about the derivations. Feel free to discuss. You just need to check how they have the acceptance rejection. As for the details, maybe not now. You can check after classes. Sure, you can have the slides and then you can check slides, how we have the acceptance rejection. So Patrick is you, right? And your name? Jerry. Okay, Jerry. Jackie. All right, so up to now about acceptance rejection applied to gamma. So any questions? Enzo? No? Okay. And Sean? What do you think about the application of acceptance rejection to gamma? Okay. And Jerry? Any questions about application of AR to gamma? No comments. Okay. And Vincent? No. And Shu? Any comments? Shu? Working on it. Okay. So here I should let you know it's acceptance rejection. But what is the difficulty? The difficulty is finding majorizing function. But I will ask you to derive this. No, actually no. I just let you feel, okay, it's acceptance rejection. Finally, if you want to apply, okay, algorithm 1 and algorithm 2 for 2 cases, and that's all. But you need to keep in mind it's majorizing function. You need to find a suitable majorizing function. Therefore, you can refer to the task book. You will have to wait to derive the majorizing function. That's it. So for this, I think that you feel. What that means, I ask you to struggle. After struggling, then you will feel, oh, okay, it's acceptance rejection, and that's all. So it doesn't mean I will that you derive how to have the majorizing function for gamma and then to have all the results there. No, it just asks you, oh, okay, the story behind gamma is acceptance rejection, and you need to know some of the facts there. All right, so this is gamma. And next one, well, I think you know the result because we have the example. So we can go to the next one. And normal. Normal actually, can we apply the previous results? No. Normal is a different story. And right now, normal we have this. Then you can have the description here. Yeah, someone tried to have the derivation. Yeah, it's true. Normal actually can follow the way to have the generation, but we don't have any methodology discussed previously to be applied to the current generation. No. So the current one similar to gamma, you just use it if you want to generate normal. All right. So we don't have any previous one, but if we have normal, then we can pass on the special property normal and the log normal. And this is the algorithm. But we have the relationship to have the parameter. Parameter of log normal and parameter of normal. So it says, in fact, look at this. In fact, x follows log normal with a parameter mu and sigma square. So we will have a mu prime and the sigma prime square. And this is the results who have the normal. If we can have the relationship, then we can generate normal. Based on normal, we can have the generation of log normal. As for the relationship, you can compare. I just mentioned this is a relationship. Once we have the relationship, it doesn't matter. We can generate y follow normal, and so that we can have log normal. Oh, sorry, maybe I need to rearrange it. Mu prime and oh yeah, true. This one mu and sigma square for the original one, but we have the relationship and how to have the result. So I mentioned this. You can find the table to know the relationship. And beta, likewise, we pass on gamma. Gamma, actually, we can pass on acceptance rejection. Even previously, we can pass on acceptance rejection to generate beta, but this time, we pass on the special property. We mentioned that, so you can apply it. As for the others, I skip them. You can try to check all of the results here of the test book. But I mentioned, you see, we can pass on special property. Same special property. And this one, pass on the current description. It's inverse transform. So you can try it again. And Johnson actually special property. Here we have a special property. Triangular. Triangular here, we have the inverse transform. Actually, we have the example previously. Triangular, actually, we can pass on current one, inverse transform. How about composition? Is it possible to apply composition to triangular? It's possible, right? Composition. So composition, that you have 1 minute to check composition. Specifically, the example previously about composition for triangular. So 1 minute to find that example. Triangular and composition. So let me measure triangular composition. Find it, raise your hands. If you can find the example for triangular and composition, yes, and raise your hands. Santari, Tobias, Sue, okay, good one, find it. So you can check it, and good too. Anyone find the composition and the triangular? Do it. And Sean, find it, the example previously for triangular and composition. And Ulis. And Gufo, find it. Okay. And Gufai. Okay, good. And good too. Try to find it and review. Same, 1 minute to review for the triangular layer. Triangular and composition. So this is a possible application of a composition. Finally, is it possible to have the convolution? Convolution to be applied to generate triangular? The answer is yes, same. Try to find the example of convolution so that you can have the generation for triangular. Okay, go and check it. So this time I just want to make sure. If you can find it, let me know. So good one. Any member? Okay, yes. And good two? Okay, yes. And good three? Yes. And good four? Yes. And good five? Yes. All right, so you can follow the way to check them. So I just want to mention triangular. Actually, we can apply inverse transform, composition, convolution, right? So finally, let me ask you one question. Is it possible to apply a projection to the current triangular solution? If yes, raise your hands. No, and raise your hands. So let me mention this again, ask you again. Can we apply a substance rejection to generate triangular distribution? Let it have a few seconds to have the decision. If yes, then later you can raise your hand. If no, sure, you disagree. So let me measure this again. Can we apply a substance rejection algorithm to a triangular? If yes, raise your hands. Okay, 1, 2, 3, 4, 5, 6, 7, maybe 8. Okay, yes, the answer is yes. Why? Even it doesn't matter, but we can apply. For example, okay, we can have a triangular here. And for example, we can try uniform. Right? Beta find uniform to have for the substance rejection. For triangular, likewise, you can find uniform. Am I right? So it's possible to apply a substance rejection to generate triangular random variable. So it's okay. All right. So triangular, we can have at least method of inverse transform, method of composition, method of convolution, and method of substance rejection. In fact, for the others, if you can apply, that's okay. But why we don't want to apply a substance rejection to generate random variable? Why? The answer is easy. Because it's feasible to apply inverse transform. So it won't be necessary to apply a substance rejection to this kind of distribution. Just for this reason. So we don't mention that. All right, that's all. So this is the generation of continuous random variables by using the method we already have. Only one exceptional case, normal distribution, we don't have the method for you. All right, we have it directly. And actually, normal, we have the method, it's called the polar method. The way to generate the normal is polar method, but we don't mention that one. Actually, you can follow the description for normal, and also you can look up normal and the normal random variable generation. Then you can find the method on the internet. Actually, follow the idea of the method provision. You will know, okay, if we can use it, at least we need to prove it. It's okay to use that way to generate the random variable. All right, so that's all. And before we have the discussion about empirical, let me make sure about the contains random variable. Any questions? No, right? If so, empirical distribution, which method we can apply? Acceptance rejection? You still have question, right? Normally, it's the inverse transform. So, inverse transform, is it true? This one. Why? Because we have a CDF. So we can try to have a CDF by given a U. So how to have the relationship based on, oh, okay, given U, then we can have the corresponding S. So it's inverse transform. And likewise for the good one, it's inverse transform. But you need to pass on the previous equation to find the relationship to return S, and that's all. So this one, I think, allow you to have 2 minutes to pass on. Maybe you can check this first. Oh, sorry, not this one. Pass on the second one. The interpolation, you can find the formula for interpolation in empirical one, and so that find how to have the relationship S based on this. Actually, the first one is easy, so I ask you to check the second one. So find the formula for interpolation for empirical group 1 and the second one, and find the formula related to G. And think about given U to CDF how to have for this. So find and try to check it. In fact, it's inverse transform. So first of all, let me make sure. Group 1, can you find the results for empirical one for the group 1? Group version. CDF in terms of G. Can you find it? Okay, and group 2? Found the slides. Pass on the slides. And group 3? No. And group 4? The interpolation. And group 5? No. So you can continue, but I just want to mention, we can pass on CDF for empirical distribution and set U equal to the CDF, and then you can solve the equation to have further formula here. Just it. So you can find it further. I just mentioned this is a way to have the result. And let us take a break for 10 minutes first. Okay, take a break. Before we continue, you can scan the QR code to join Present Live if necessary. So this one, actually, you can refer to chapter 6. Chapter 6 talking about empirical distribution. Then you can find CDF. Once you have a CDF, likewise, you have the relationship. CDF set it to you, and then you can solve the equation. The equation, what does it have for the formula X? So that's why we can pass on inverse transform method to have further generation of this. So you can check it. So this is the result using inverse transform for empirical distribution. I think inverse transform, you still can try. All right, so here we have another poll. Up to now, so the question here is still thing unclear. If you still need to ask me to re-explain, you can show something here. And let me check. Can you see it? No? Yes or no? So up to now, no. That's good. But let me measure not finished and raise your hands. So all finished, right? So let me move on to the next one. Here. Oh, sorry, not this one, sorry. And how about this attendance checking today? Can you see it? Okay. Again, let me measure, not finished, and then raise your hands. Okay, so let me go to the next one. So up to now, we can pass on inverse transform as this to have the generation to the continuous random variables and empirical random variable. But how about discrete random variable? The idea is still okay, inverse transform, but we have some special treatment. You see? We still can apply inverse transform, but later we will have a new method we call Alias method. Actually, Alias method coming from acceptance rejection. So we still can have acceptance rejection. So all can be applied possibly, but Let us check case by case. So first of all, for the arbitrary discrete distribution, let's say, oh, we can have the PMF here. How to generate these? And right now we assume we have an index from 0 to n. We assume from 0 to n. So how to have the generation? Actually, we can follow, okay, we have J follow that, okay, sorry. We assume we can have the generation for that, but right now, we want to have the generation for 1 to m. So we can have a shift, is it okay? So this one, just let you know, okay, we have a shift. So that's why we have the version, shifty version. So the current one, we assume if we can generate J from 0 to n, and right now we want to have a shift. So this is a way to have the shifty version. So for this one, I think you know that one for sure. But we want to have the further discussion. All right, the general one, maybe we consider 0, 1, 2, 3. So right now, assumption J, right now we want to have the generation for this assumption. 0 equal to 0.15 and 1, 2, and 3. So any idea to have the generation? The current idea says, okay, we can have the array, 100 array, to store number 000 from 1 to 15. Why? Because two digits after the decimal point. So we have a 100 to store. So 15 zeros, 20 ones, and then 37 twos. Finally, it's 28 threes. So that's why we have the arrangement for array from 1 to 100. Is it okay? All right, and then the algorithm says if we have the weight, the algorithm says we need to have an index J. J actually fall in between 1 to 100. For example, 7. 7, we have the content 0. So we return 0 to x. And that's it. So the current idea, we store the value of 0, 1, 2, 3 in array. And we look up the content in the array and then use that content to serve as a value for x. And that's it. So this one is easy, right? But about this, I think previously you know this, how to have the index, right? 100 multiply u, taking floor plus 1. Then we have integer from 1, uniform, discrete uniform from 1 to 100. So this is, it should be okay, right? So about this, not okay, raise your hands. All right, so this is the first approach to generate these. This J. All right, this J we have for the interval 0 to n. So here n is 3, right? And this one we call its table lookup. Sorry, I forgot to mention the name. This one is table lookup. Why? We look up the content in the array, and so that it's called the table lookup. And next one, we want to have the efficient approach. Why? Simple, but simple maybe somehow fast, but sometimes we need to have the more storage to store the content. So can we enhance it? Yes, we have the enhanced version, this one. Mercaglia tables. Right now, we still have the same example, but we ask you to check we have the individual position, tens factor, and the hundreds factor. So tens factor 1, 2, tens factor we have 1, 1, 0, and 1 we have 2, and 2 we have 3, and 3 we have 2. That's correct, right? And we have 1, 2, 3, 4, 5, 6, 7, and 8. And 1 over 8 is 0. 2 over 8 is 1. 3 over 8 is 3. And the same, 2 over 8 is 3, right? So we can have the corresponding probability. And how about hundreds factor? We can have 5 zeros. 0, 1, and 7 twos, and 8 threes. And so that you can have 5 plus 7 plus 8, and 1 over the total number, 5 over total number. This is a corresponding probability. All right. And also, if we find the corresponding ratio, the ratio to have a tens factor and ratio to have a hundreds factor, so that what's the probability? You can have the corresponding probability, corresponding probability, corresponding probability, and corresponding probability. So we have these. If we pick hundreds factor, the probability should be 0.8. Only probability 0.2 pick the hundreds factor. Why? According to the probability of hundreds factor and the probability of tens factor. So we have 0.8 and 0.2. And right now, the story here, how about generate 2? Generate 2, you can pick tens factor, or you can pick hundreds factor. If tens factor, the corresponding probability should be 3 over 8, and the 2 should be 7 over 20 in hundreds factor. And finally, same, the probability should be the original probability. So if we have the way to have the generation, finally we can have the algorithm here. You can pick tens factor. According to the ratio, then you can generate a corresponding 0, 1, 2, 3, or just 3. And likewise, hundreds factor. If you can have, for example, thousands factor, you still can continue. And that's it. So this is a current algorithm, Masaccio tables algorithm. For this one, I think you can refer to the slides, and also you can refer to the current slides here. I mean, you can refer to the file, or you can refer to the current one. If you fail to have the slides, you can take a picture, this one, or this one. I think maybe you can have the slides. Allow you to have 2 minutes to check. And also, you can discuss with your members about the current one, Masaccio tables. So about molecular tables, any questions? For Willy? No. And Ulis? No. All right, so we can continue. Of course, this one can set space, right? And the final one is the improved version of acceptance rejection. All right, acceptance rejection we have for the algorithm here. So you can check it first. About the table, let me check any table and let me put it to the line group. So wait a moment. You can check this one for 2 minutes first. The algorithm for AR, so that we have the so-called method, Alias method. Continue. The Alias here says we have the alternative. So, sorry, I want to find the setup, but right now you can take a picture for this. Later we will are using. So I use our line group to take a photo for these. So you can refer to the setup. The setup says, oh, okay, we have L and we have F. So how to set? Initially, authority set it to itself. And the cutoff value set it to 0. 0 says impossible. Always refer to myself. Initially, we have that. And we have the calculation for B sub I. B sub I says the difference. My target probability and minus the uniform probability. Right? Because start from 0. 0, 1, 2, 3 to n. Of course, we have n plus 1. So the current value authority says the A is set to itself. And cutoff value set it to 0. Impossible to use the current way. Just use the authority itself. And this is the difference. And later we can have the algorithm C find the minimum one. The minimum says we have negative. Negative, then minimum one. So the most, actually the smallest one in terms of negative value. And K, actually, the other one is maximum value. So, negative value, positive value, find the maximum one. And minimum one. In fact, this is a maximum one if we remove negative sign. And this is the largest one because it's positive. And then we can swap. Oh, okay, smallest one and largest one. So, how to do? We allow index is D, and the N denote the largest one, and K denote the smallest one. And then what to do? Actually, we want to that L sub K, K with the smallest value, K direct to N. And here it's really special. Well, why we set FK follow the way? Later you can check it. But someone like K borrow all the possible quota from N. Borrow the quota from N, then we have this. Basically, the smallest one denoted by C. The value denoted by C. So borrow from N. So here it's minus. So someone like B plus C means minus. So I borrow my, for example, my quota to K. Someone like quota. And so that we can repeat, borrow a quota, so you need to refer to me, it's N. So how to refer to N using the probability here, but why? Right? Why? Maybe we should have the reason, but you can look up later. Why? And also ask you to squeeze out. Some of you mentioned, okay, about the good discussion. Sometimes some problems difficult. And later I already have a problem like this. You can find any results from the internet or maybe from ChatGPT, but you should have your own way. And why? Actually, I have a problem like that. So later I will ask you to check. Before that, initially, we have some story like this. Uniform, 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 uniform. But this is a true story. The true story says, okay, we can have the gap to a quarter. You see, a quarter. I don't have enough one. I want to borrow. Where I can borrow, I borrow from 1. So this is a story between 0 and 1. Likewise, we can have the story between 2 and 3. I don't have enough quota, so I borrow the quota from 3. So for the 2 figures, can you accept the story here? Right? If so, then it says about M here, and about K here, and this is C. And this is D. And likewise, we can have the story, this is C. Maybe first one and second one. And so that the algorithm can stop. So refer to your algorithm. So previously I asked you to have the algorithm take the picture. Maybe right now if you don't have the picture, you can look at the picture on line group. Line group says we should have an index. Initially we have a k index, k equal to 0, m equal to 1. Why? We have a difference, positive 1. We have a difference, minus 1. The largest one is D, the smallest one is C. But smallest one C means the largest gap. Right, the largest gap to a quarter. So we borrow from 1. And for the current story, okay, just math. Right? So we can borrow entirely from 1 and then finish. And likewise, we can have the story for 2 and 3. And that's all. So, this is a true story. But right now, we have the algorithm. So, right now, the algorithm actually initially we have this, right? Given. And no. So, right now, someone like, oh, okay, I reverse them. So, this time. Then you have 5 minutes and discuss with your neighbor how to have the table. Based on the previous algorithm. Maybe 5 minutes is quite long, but allow you to have 5 minutes. Generate the table based on the given algorithm. So show it. And of course, feel free to discuss. So maybe you can work on for yourself first. And if you cannot have it, later you can discuss. So each one try to find the table. Allow you to have 5 minutes. So go and study. If you fail to have the algorithm, you can look up the table, the algorithm on our line group. So go and check it. Initially, I just asked you to carry out based on the algorithm. Based on the algorithm. finish finding the table? No. No. Yes or no? Alias says we have extremely small. For example, after then you can set it to, for example, this one. Really small. For example, 10 raised power to minus 4. So then you have 3 more minutes to finish the implementation to find a table. Currently, you are asked to carry out the algorithm to find the table. So again, let me make sure finish. Can you have the table here? Group 3 finish. And any other member finish to have the current table? Group 4? Yes. Right, yes. And group 5? Yes or no? No. And group 2? Yes or no? No. And group 1? Yes. So 2 groups fail to have the result, but it's still okay. So it says you can pass on the algorithm to have the result. In fact, the step here, 1.1 here and 1.2 here. 1.1 for 1 and 2. So 0 and 1, and 1.2 for 2 and 3, right? Because the step 1 gap should be minus 0.15. positive 0.15, 0.05 and minus 1, and positive 0.05. And choose the smallest one and largest one. It's 0 and 1. 0 and 1, all we need to do, borrow the gap. So finally, bj becomes 0, and bj becomes 0 for 1. So we have the setting for f0 set it to 1, and how to have a cutoff value. Value says, So we can have the setting for this because I just care about, I didn't have the results already. So here, how to set the value. The value set it to 1 plus. So finally it's right. So correct, and no change. I like how I same story apply to this. So cutoff value 3 and how to set this one. Right? So have it, that's all. So about the quick discussion, good 1 is okay. Sound 3, good 3, and good 4. And right now, good 2 and 5 is okay. Follow algorithm. So you should follow algorithm. And so you can have this. And this, what is the result? It's 1 plus c multiply n plus 1. So n currently is 3. So the denominator sum of the member from good 2 ifs is okay. And Patrick, is it okay? Okay, so if so, I just follow the algorithm. As for the reason, why? Why we have an algorithm like that? Once we finish all, then we can return to let you know the story. In fact, the story says, initially we think all are even. Somehow like humans have the equal right. So all are equal. But in reality, no, not fair. So maybe a bit higher, a bit lower. But someone like, if you cannot have the equal value, you can borrow some from the other with more. So here we have the story. And right now, second step. Here, step 1. Building the table. And step 2, checking is it true. And right now, if we based on the table and also based on the Alias method here. So Alias method, how to have the generation. So you can refer to Alias method based on the slides. So how to have a 2? 2, if you want to have a 2, only choose index 2 and yield more than or equal to this, and so that we stay here. Two says, to stay here, to stay, still have the original index lower than or equal to cutoff value, f sub I. So look at the table here. First of all, based on the current table, if we just want to have 2, Alias no 2. So it says 2 only choose 2 and use 2 itself. So the condition should be uniform value lower than or equal to the cutoff value. The current cutoff value should be 0.8, right? So that's the story. Choose to pick index 2 and the state to choose 2. And the corresponding probability should be a quarter multiplied the corresponding probability 0.8. Finally, the probability should be 0.2. Same as the original setting? Yes. And how about generating 3? 3 can be choose 2, but greater than 0.8. Right? Or choose 3 and itself. So we have 2 to Alice, but actually here you can check our slides and so you know the value. Finally, is yes. All right. So how to have the setting? 0.3, we choose 2. But the probability greater than 0.8. And choose 3 and itself. So we have the probability. Right, as desired. So first one, choose 2, but the probability greater than 0.8. The probability should be 0.2. And the second one, choose 3 and itself. So we have the whole, so it's probability 1. So finally, the probability should be 0.3 as desired. Okay, so here. All right, that's all. So this is the checking. About the checking, any questions? No, right? So if so, let me refresh it. So this is the example. But let us continue. So up to now, we already have a table lookup, Massac-Leo table, and Alias method to have the generation. And let us move on to have the further generation. How about binomial? Bernoulli is easy, right? How to generate Bernoulli? If we have a P, it's uniform U, lower than or equal to P, then return value, maybe it's 0, or otherwise return another value. So Bernoulli is easy. But right now, okay. But right now, let's check binomial. Binomial, what's the current result? It's the special property. Can you accept that? So we should pass on Bernoulli. Bernoulli, then, we can have Bernoulli and then some of the results. So this is a special property. I just said no, it's the special property. You can check the special property between Bernoulli and binomial. And geometric, right now we don't pass on the special property. Instead, we pass on inverse transform. So inverse transform this way. So that says you need to have the CDF first and then set value U to CDF, then you can find the result. Likewise, Idiagonal and skip it, you can check it. And negative binomial, it's a special property because we can pass on geometry and then geometry, sum of a geometry can result in the negative binomial, right? Special property. So the special property says it's convolution, relationship or convolution. And next one is Poisson. Poisson actually here we pass on inverse transform. By inverse transform, we need to have a formula, and this is a formula to have the result. So it's an inverse transform. And that's all. So right now, I already have the good discussion. Refer to our previous setting. But what's the problem? I ask you why. We have the story to FK. And so that we can have the exact result. So You can scan the QR code here, or maybe, sorry, let me rearrange it. So wait a moment. So let me set up first. So maybe everything's okay. So you can scan, oh, sorry. So I already have the good discussion now, and you can check line group so that you have a pattern. And also, let me move on to the next one. So this one. So we have a pattern. You can check our line group. And answer this first. Same, before 4 p.m. Let me have your own answer. And maybe some of you feel, okay, it's difficult, but at least if you have the answer, you have 4 points at least, right? 4. If you have the correct answer, then you will have 5 points. So do your best to have the answer before 4 p.m. Okay. So finish this one first and also check Padley to know the answer. So then we have 5 minutes first to have the discussion with your neighbors. And also you are allowed to use any tool. For example, ChatGPT. You should key in the key terms. So this one is easy. Just let me know, okay, check my answer on Padley later. Just one question. I ask you to squeeze out, oh, okay, why? So don't forget to return your answer before 4 p.m. Even your answer is wrong, you still can have 4 points, right? And recently, maybe for some reason, we we don't finish the recording. So I will ask TA to finish this as soon as possible. Actually, I'm the bottleneck. So you can have the discussion with your neighbors first for 5 minutes. So feel free to have the conversation with your members. So let me measure this one not finished. Not finished, raise your hands. Because I see 7, okay. Finish it first. For example, you can type, see my answer on Padlet. So can you find any possible solution from the internet? Yeah, sure, you can check. So Ben, any possible solution from the internet?
I'm asking GPT.
Oh, sure. And likewise for Ulis, can you find any possible solution? Okay. And Valentine, you can try ChatGPT or Google. So any possible solution?
Yeah, I'm trying to use GPT.
Sure. So let me mention this again. Try to finalize this. So not finished? Good one. All finished, right? Good 2. And good 3. And good 4. Finish, right? And good 5. Okay, so finish that. I can move on to the previous one. So that is how for 5 more minutes to discuss this. So why that way, this way? Why it's 1 minus c multiply n plus 1? In fact, the setting here is just about the quota. I borrow the quota from which one? So it's not mine. For the portion should be referred to that one. This is a key idea. And so they will know, okay, the real one should be referred to that. Even you have the solution from ChatGPT, you need to make sure correct or not. And even it's correct, you should understand why. And next week we have a case study. I will provide you some recorded video. So that we will have a style of the classroom. I have some selected paper. And because of the classroom, I will ask you some questions. So next week we have a style like that. The classroom style to share case studies. So let me measure any possible solution. Good one. So let me have a look at that. Okay, so maybe you can try. And how about yours?
No, not yet.
Okay, you have it? Okay, you can try. And good to any possible solution? Yes or no?
Yes.
Let me have a look at that.
We're trying to understand it.
Okay, you can try. And group 3? Any possible solution? Okay, let me look at that. Oh, I think all of you find from the same source. Okay, so you can try from the same source, but it doesn't mean I ask you to use copy and paste. Correct or not, you need to judge. And how about yours?
Maybe I got the answer on ChatGPT.
Sure, so you can try. So can you show me the answer from ChatGPT?
Here's the answer.
Let me have a look at this. Okay, you can try. But correct or not, you can make sure. And good fight. So I think maybe after checking answer from all possible, maybe from almost the same source. But correct or not, I'm not sure. You can try. And you can try to have the reason. Okay, why? Reasonable or not, you can judge. But the real story here should be, for example, 0, 1, 2, and 3. Initially, we pretend we have the equal probability. But finally, no. Someone like, oh, I'm really short. And the other guy are really high. I should borrow something from the tall guy. And so that I have something. But we have a shorter quantity. The shorter quantity should be referred to that taller guy. So this is a true story. Based on the true story, if you can have the reasonable reason to explain, then possibly that answer is the correct one. So you can check them. And maybe just a few minutes to the 15, 20, and then we need to dismiss the class. But I think almost up, and allow you to have a time to same 4 p.m. today to upload your answer. At least you have 4 points even you have the wrong answer. If you can have the perfect one, then you can have 5 points because of the correct answer. Well, that's it. This is the almost the good, maybe possibly I may have the other, but almost the final good discussion. So if no further questions, no further question, that's call it a day, right? And don't forget to upload your answer before 4 p.m. All right. Okay, that's it. And see you next week. And next week, we can get this done soon because we just have a few parts of the results. And some I will go through quickly. And finally, we will reach the case study. So we will finish it next week. And about the final exam, yeah, it's true, 2 weeks later. All right, that's it. See you. Bye-bye.